we turn our attention to multiple writer, multiple reader algorithm in the fail-silent model. If we go back to single writer, multiple reader, we used a read-impose majority voting strategy. If we just try to use the same algorithm as in the single writer case, multiple writers might have non-synchronized timestamps. And here is an example. We have 3 processes. P3 writes the value 5 with a timestamp 30. It gets an acknowledgement and finishes the write. But a later write, as you can see here, this writer might have an old timestamp, 28. In this case, we have this write has a response before this write, but it will be ordered in the order of the timestamps, so this is not linearizable. So we have to synchronize our timestamps in this algorithm. So we add a new phase, and we call the algorithm read impose write consult majority. And before writing, we do a read from a majority to get the last timestamp. And this means that we do a query phase to get the latest timestamp before the update phase. So now we have an algorithm that in the write, we do 2 phases, a query phase and then an update phase. But of course, if we take the timestamp as it is, 2 concurrent writes might have the same timestamp. But this is easy. We just compare the process identifiers to break the ties. So our timestamp now is actually a pair, a timestamp and a PID, which is used to break ties. So initially, the value of each register has a timestamp initially 0, and the process identifier, we are assuming that we are talking about process PI. So the process identifier is I, and the initial value for whatever type this register has. So let us now look to the write operation. The read operation is exactly the same as before in the read impose algorithm. So we just need to change the write operation. The write operation has both now a query phase and an update phase. So the process starts with the query phase. So PI starts with the query phase and send a query request with the register identifier R. PJ responds to the query with its current timestamp PID that it has stored. When the query phase ends, PI picks the max timestamp PID received. This is the max one. And now the process starts an update phase. And in the update phase, it takes the timestamp, increment it, and add its own processor identifier. So in the update phase, we start by sending an update request for register R with this timestamp value pair, timestamp value pair. So here is the process identifier, here is the incremented timestamp, and here is the value that this process wants to write. Every other process, as usual, updates its register to the max of the current value of the register and the value received in the message. And it responds with an acknowledgement. And of course, PI then completes the write phase when the update phase ends. So as we can see from this figure, we have an update phase here. This update phase ends here. And then the process starts a query phase here. And this query phase, when it ends, the write is complete. Now, our algorithm, as a summary, it does read impose, write consult majority. It has this new update phase. Before writing, it reads from majority to get the last timestamp. and observe that in all phases, any process Pi sends acknowledgement even if Pi receives an update request of an old timestamp. It will not update its register, it will just send the acknowledgement. And in fact, this was not necessary in the case of single writer algorithm. But because we are in a multiple writer situation, we can get the following execution scenario. So here's an example to see what happens if we don't send acknowledgement. We have a slow process, P1, that does an update and waits for acknowledgement. Then we have a fast process, P2, that does another write and receives acknowledgement from a majority. Now P1 does not get enough acknowledgements if the nodes ignore the write 5 request, and it can stall. So it is important to always send the acknowledgement in the update phase. This algorithm terminates because no processor will stall or wait forever. And in this case, we say that the algorithm is wait-free. Every correct process should make progress. No one will stall. We have no deadlocks, no live locks, and no starvations. This ends the description of the atomic register. We will get much more deeper understanding in the next unit when we look to the correctness of the algorithm. As just a summary of the performance of the algorithm for atomic register, a write to complete requires 2 round trips. One to inquire about the timestamp, that's the query phase, and one to the broadcast ACK phase, which is the update phase. And the read requires 2 round trips to complete. One also is a query phase to read, and the other to impose the value read if necessary.